Long ago, before anyone could truly see the stars as we do now, a few curious minds began to imagine something extraordinary. A place so heavy, so dense, that even light could not escape its pull. They called it a dark star. It was only a dream then, an idea drawn from gravity and imagination, centuries before the tools or the theories existed to prove it. But that dream would one day become reality. Today, we know these invisible regions as black holes, not objects in the usual sense, but boundaries in space where the known laws of physics simply stop. Each one contains a heart of infinite density, a singularity, surrounded by a boundary called the event horizon, the point of no return. Imagine standing at the edge of a vast cosmic waterfall. Space itself is the river, flowing faster and faster. At first, you could still swim against the current, but closer to the edge, the flow becomes too strong. And once you cross that threshold, not even light, the fastest traveler in existence, can climb back out. That invisible edge is the event horizon. Many of these strange regions begin their lives in violence. When a massive star runs out of its nuclear fuel, its own gravity crushes it inward, collapsing its core into an incredibly dense point. The outer layers explode in a brilliant supernova, leaving behind only the ghost of the star, a black hole, silent and cold where a sun once burned. Time itself begins to behave differently around such a place. Einstein taught us that gravity and time are woven together. The stronger the gravity, the slower time passes. Near a black hole, this effect becomes almost unimaginable. To someone watching from afar, the seconds near its edge stretch endlessly, as if frozen. But for the traveler drifting closer, time feels normal, one heartbeat after another, even as the rest of the universe races ahead. It's easy to picture black holes as hungry monsters sucking everything in. But in truth, they are more subtle than that. If our sun were replaced by a black hole of equal mass, the Earth would continue its orbit almost exactly as it does now, only in darkness. From a distance, the pull of gravity would feel the same. It's only when you approach the edge that space begins to twist and fold. The name black hole itself is quite new. It was first spoken aloud by the physicist John Archibald Wheeler in the late 1960s. Simple words, yet they carried the weight of something infinite, a hole in the fabric of reality. And these holes are not rare. Our own galaxy, the Milky Way, is thought to harbor hundreds of millions of them, quiet remnants of long-dead stars scattered invisibly across the night sky. We don't see them, but we feel their presence in the way nearby stars move, the way gas clouds swirl and vanish. At the center of the Milky Way, far beyond the glow of every familiar constellation, lies a much larger one, a supermassive black hole known as Sagittarius A star. It is 4 million times more massive than our Sun, and yet it sits in perfect silence, anchoring the galaxy itself, holding the spiral of stars in its gravitational embrace. Sometimes these giants find each other, two black holes circling in a slow cosmic dance. They spiral closer and closer, sending out invisible ripples through the very fabric of space-time. Those ripples are called gravitational waves, faint echoes of titanic motion. When the two finally collide, they release more energy in that single moment than all the stars in the universe combined. For a long time, this was only theory, but in 2015, delicate instruments on Earth trembled ever so slightly, recording the first whispers of those waves. We had, for the first time, heard two black holes merge, a sound older than life, traveling 1 billion years to reach us. A black hole itself emits no light. That is why it appears so perfectly black. Not even a glimmer can escape its gravity. And yet, the space around it can blaze with brilliance. As gas and dust spiral inward, they form a radiant disk that burns hotter than any star, glowing in X-rays and ultraviolet light. This glowing halo is called an accretion disk, one of the brightest sights in the universe, born from the darkest heart imaginable. Many black holes spin. In fact, some spin so fast that they drag space and time around with them, twisting reality like a whirlpool in a river. The faster they spin, the more the universe itself seems to bend to their motion. Even though nothing escapes from within, the regions near the edge can launch powerful streams of energy that shoot across galaxies, jets of particles moving close to the speed of light. These jets can stretch for thousands of light years, carving shapes in interstellar gas and even sparking the birth of new stars. And while the black hole remains invisible, the light that swirls around it gives us clues. In 2019, a network of telescopes around the world captured the first real image of a black hole's shadow, the one at the center of galaxy M87. It appeared as a glowing ring of orange light surrounding a dark core, humanity's first direct glimpse into the unknown. That black hole was enormous, more than 6.5 billion times the mass of our Sun. Its event horizon was so vast that light itself would need almost 2 days to make a single loop around it. If it were placed where our Sun is now, its dark shadow would stretch beyond the orbit of Neptune. And yet, even these cosmic titans are not eternal. In the 1970s, Stephen Hawking made a discovery that changed everything. Black holes can slowly lose energy through a delicate quantum process now called Hawking radiation. They evaporate molecule by molecule, particle by particle, until eventually, over unimaginable spans of time, they fade away completely. So even the greatest forces in the universe obey the same quiet truth as everything else, that nothing lasts forever. Stars are born, they live, they die, and even darkness itself has an ending. The universe is full of light. Every point of brightness in the night sky is a story unfolding across time, a story of creation, transformation, and, eventually, collapse. Stars are the engines that have shaped the cosmos, the furnaces that forge the elements, and the seeds from which black holes are born. To understand black holes, we must first understand the lives of stars, because it is in their final moments that these mysterious objects come into existence. A star begins as a cloud of gas and dust. In the cold expanses between stars, enormous clouds float silently through space, their hydrogen atoms drifting for millions of years. Over time, small movements, collisions, and the subtle pull of gravity cause parts of these clouds to clump together. As these clumps grow denser, their gravity strengthens, drawing in even more material. Eventually, the cloud collapses under its own weight, and the temperature at the center begins to rise. This is the birth of a star. When the core becomes hot enough, something extraordinary happens. Hydrogen atoms, under immense pressure, begin to fuse together to form helium. This process, nuclear fusion, releases tremendous energy, and that energy pushes outward, balancing the inward pull of gravity. The star stabilizes, its surface begins to glow, and a new light appears in the universe. This stage, called the main sequence, can last for billions of years. During this time, the star lives in harmony. The energy from fusion keeps it stable and shining brightly. For smaller stars like our Sun, the fusion of hydrogen into helium is a slow, steady process. For larger stars, many times the mass of the Sun, fusion occurs more rapidly and violently. The larger a star is, the faster it burns its fuel and the shorter its life becomes. A small star might live for tens of billions of years, while a massive star may last only a few million. Inside the core, the star is constantly changing. As hydrogen is consumed, helium begins to build up. When hydrogen runs low, the delicate balance between pressure and gravity pushes inward, and the star begins to contract. As the core contracts, it heats up again, and new forms of fusion begin. Helium atoms fuse into heavier elements, carbon, oxygen, and beyond. In the most massive stars, this process continues, creating elements all the way up to iron. Iron is different. When fusion produces iron, it no longer releases energy. Instead, it absorbs it. At this point, the star's core can no longer support the weight pressing down from above. Without the outward push of fusion, gravity takes control. The core collapses in a fraction of a second, and the outer layers of the star fall inward at tremendous speeds. The result is one of the most violent events in the universe, a supernova. The collapsing core rebounds, sending shockwaves racing through the star's outer layers. The explosion tears the star apart, releasing more energy in a few seconds than the Sun will produce in its entire lifetime. For a brief time, the dying star can outshine an entire galaxy. It is in this final act of destruction that new elements, gold, silver, uranium, and others, are formed and scattered across space. These elements will someday become part of new stars, planets, and even life itself. But the core that remains after the explosion does not vanish. What happens next depends on the mass of that core. If it is relatively small, it becomes a neutron star, an object so dense that a single teaspoon of its material would weigh billions of tons. If the core is more massive still, gravity continues to collapse it beyond the point where even neutrons can resist. Nothing can stop it from falling inward. The matter is crushed into an infinitely dense point, a singularity. The space around it warps so completely that not even light can escape. A black hole is born. The transformation from a star to a black hole is both tragic and awe-inspiring. A body that once gave light to the universe becomes something that traps light forever. Yet this death is not an ending, it is part of a greater cosmic cycle. Black holes, though invisible, shape the galaxies around them. They are the remnants of stars that once illuminated the cosmos, now continuing their influence in darkness. Black holes formed from single massive stars are called stellar mass black holes. They typically contain a few times the mass of the Sun, but are compressed into a region no larger than a city. If you were to replace the Sun with a black hole of equal mass, Earth would continue to orbit it just as it does now. The gravitational pull would be the same. The difference is that the black hole emits no light, no warmth, no solar wind. It would be a silent center of gravity, invisible against the dark background of space. Some black holes do not exist alone. Many live in binary systems, paired with a companion star. In such pairs, the black hole's gravity draws matter away from its companion, forming a swirling disk of hot gas around it. As this gas spirals inward, friction and pressure heat it to incredible temperatures, and it emits powerful X-rays. Even though we cannot see the black hole itself, we can detect these X-rays and know that something invisible and massive lies at the center. Over time, as the black hole feeds, it grows larger. The more mass it consumes, the stronger its gravity becomes. Sometimes, two black holes that formed separately can eventually come together. If they are born in the same region of space, or after galaxies collide, their orbits can decay over millions of years. They spiral toward one another, losing energy in the form of gravitational waves, ripples in the very fabric of spacetime. When they finally merge, they form a single, larger black hole, and a burst of gravitational energy radiates outward. Gravitational waves are one of the most remarkable discoveries in modern astrophysics. First predicted by Albert Einstein in 1916, they were not detected directly until a century later. In 2015, the collision of two black holes, more than 1 billion light-years away, sent tiny distortions through spacetime, expanding and contracting the distance between objects on Earth by less than the width of a proton. This detection confirmed one of Einstein's last untested predictions and opened a new window on the universe. Through these waves, we can now listen to the cosmos in a way that was once impossible. Each merger of black holes creates a distinct signature, a brief, fading vibration that tells us about their masses, their spin, and their distance. The universe, once thought to be silent, is alive with the sound of gravity itself. But long before humans built detectors or telescopes, the story of these objects began in the quiet darkness of the early universe. After the first generation of stars lived and died, they left behind black holes that began to merge and grow. Some of these eventually became the supermassive black holes that now sit at the centers of galaxies. Even in those early epochs, black holes played a key role in shaping the cosmos, influencing the formation of galaxies and the distribution of matter. To this day, astronomers continue to study how black holes grow and why nearly every galaxy appears to have one at its core. It is possible that small black holes formed first. From the moment we look into the night sky, we see stories written in light. Each star, from the faintest pinprick to the brightest beacon, is a chapter in the long history of the universe. The story of black holes begins here, among the stars within the same clouds of gas and dust that gave birth to everything we see. The universe is not static. It breathes, it changes. Over billions of years, it transforms simple hydrogen, the lightest and most abundant element, into the rich diversity of matter that makes up worlds, moons, and life itself. This transformation begins when gravity takes hold of clouds of gas adrift in space. Inside these vast molecular clouds, regions begin to collapse under their own weight. The particles within fall inward, slowly gathering mass and density. As the cloud shrinks, it warms, pressure builds, atoms collide more frequently, and the very first spark of fusion ignites at the center. A star is born. For millions or even billions of years, a star lives in a delicate balance. Its gravity pulls inward, trying to crush it, while the heat from nuclear fusion pushes outward, keeping it stable. The core fuses hydrogen into helium, releasing light and heat that stream across space. This steady burning defines the main sequence, the long, stable period of the star's life. The fate of a star depends on its mass. A small star, like our Sun, will live a calm, extended life, slowly burning through its fuel. A larger star, perhaps 10 times as massive, burns much hotter and faster, exhausting its hydrogen supply in only a few million years. The larger the mass, the shorter the lifespan. As a star ages, its balance begins to falter. When hydrogen in the core is depleted, fusion slows and gravity gains ground. The core contracts and heats up, while the outer layers expand outward. The star swells, becoming a red giant or, for the larger stars, a red supergiant. In this stage, heavier elements begin to form: carbon, oxygen, silicon, even iron, the building blocks of planets and life. But there is a limit. Iron marks the end of fusion's generosity. Fusing iron does not release energy, it consumes it. When a massive star fills its core with iron, the furnace that held gravity at bay sputters and
atoms are crushed together with such force that protons and electrons combine into neutrons. The outer layers of the star, no longer supported, rush inward and rebound off the dense core. The result is an explosion of unimaginable power, a supernova. For a brief moment, a supernova can shine brighter than an entire galaxy. The shock wave races outward, scattering elements into space. These are the seeds of new worlds. Every atom of gold, calcium, and carbon that we know today was forged in such stellar deaths. The universe recycles its own material endlessly, life born from the ashes of stars. At the heart of this explosion, something extraordinary happens. If the remaining core is less than about 3 times the mass of our Sun, the collapse halts when the pressure of neutrons becomes strong enough to resist gravity. This creates a neutron star, an object so dense that a teaspoon of its matter would weigh billions of tons. But if the core is heavier still, gravity continues to crush it past the point where matter can resist. No known force can stop the collapse. Space itself curves inward and a black hole is born. This is the death of a star, yet also the beginning of something new, a region of space where gravity is absolute, where the laws of physics as we know them begin to falter. The transformation from star to black hole marks a threshold between the known and the unknown. Though black holes are invisible, their birth is often accompanied by an immense burst of radiation. As the core collapses, magnetic fields twist and amplify. Jets of high-energy particles shoot out at nearly the speed of light. These gamma-ray bursts, some lasting only seconds, are among the brightest events in the universe. They signal the birth of new black holes across the cosmos. The first black holes likely formed not long after the first stars. In the early universe, enormous stars, hundreds of times more massive than the Sun, burned briefly and died young. When they collapsed, they left behind black holes that may have grown rapidly, merging and feeding to become the supermassive giants we find in galaxies today. But not all black holes come from such titanic origins. Many are born quietly in binary systems, pairs of stars orbiting one another. When the more massive star dies first, it can leave a black hole behind, while its companion continues to shine. The two remain bound together by gravity. As time passes, the black hole may begin to draw material from its partner, forming a swirling disk of hot gas around it. This accretion disk glows brightly in X-rays, revealing the black hole's presence. Through careful observation of such systems, astronomers have been able to measure black hole masses and study their behavior. We can watch as stars orbit invisible companions, moving faster near an unseen center. These movements tell us that something incredibly massive must be there, something compact, dark, and dense beyond imagination. Even though black holes are known as destroyers, their role in the universe is far more complex. They are part of the life cycle of galaxies and stars, regulating the flow of matter and energy across cosmic time. When black holes feed, they release powerful radiation and winds that can heat or disperse gas, preventing new stars from forming. When they rest, that same gas cools and condenses, giving birth to fresh stars once more. In this way, black holes participate in the rhythm of creation and destruction that governs the cosmos. Our own galaxy bears witness to this balance. At its heart lies Sagittarius A star, a supermassive black hole about 4 million times the mass of the Sun. Surrounding it are stars moving at incredible speeds, tracing orbits that prove the black hole's existence. And yet, despite its immense gravity, Sagittarius A star is relatively calm. It feeds only occasionally, drawing in small amounts of gas and dust. Most of the time, it remains quiet, a sleeping giant at the center of our Milky Way. The relationship between stars and black holes is ancient and intimate. Stars give birth to black holes, and black holes, in turn, shape the galaxies that host new stars. This cosmic feedback ensures that the universe never stands still. It evolves through cycles of birth, growth, decay, and renewal. When we look deep into the universe, we are also looking back in time. The light from distant galaxies has traveled billions of years to reach us. Many of those galaxies appear small and irregular, their stars young and bright. At their centers, even then, black holes were already forming, feeding and influencing the stars around them. The connection between light and darkness, between life and death, was already written in the fabric of space. Even within our own galaxy, the evidence of stellar death surrounds us. The Crab Nebula, the remnant of a supernova observed on Earth in the year 1054, still glows with the energy released from that explosion nearly 1,000 years ago. At its center spins a neutron star, the collapsed core of the star that once was. The nebula is a living record of both destruction and rebirth. Such remnants tell astronomers about the forces at play in stellar collapse. By studying the composition of nebulae and the motion of their gases, scientists learn how elements are distributed through space. The very atoms that form planets, oceans, and living creatures all originate from these ancient explosions. The death of a star is the reason we exist. For all their power, most stars end their lives quietly. Smaller stars, like the Sun, lack the mass to go supernova. As they exhaust their hydrogen, they expand into red giants, shed their outer layers into space, and leave behind a white dwarf, a hot, dense core roughly the size of Earth. Over billions of years, that white dwarf cools and fades, becoming a black dwarf, a cold, dark ember marking the true end of a star's life. Even in this stillness, gravity remains constant. If a white dwarf is part of a binary system, it can draw matter from its companion, growing denser until it crosses a critical threshold. At that point, a runaway fusion reaction ignites, leading to a Type 1a supernova, a powerful explosion that leaves no remnant behind. These explosions serve as cosmic markers, allowing astronomers to measure distances across vast stretches of space. In the grand tapestry of the universe, each type of stellar death has a purpose. Supernova spread the elements that seed new stars and planets. Neutron stars and black holes reveal the extremes of physics. White dwarfs and black dwarfs remind us of the slow passage of time. Together, they form a continuous story. The story of matter transforming, cycling endlessly between light and shadow. When two neutron stars collide, they create a burst of gravitational waves and light that ripples across the cosmos. In such mergers, gold and platinum are formed, heavy elements forged in the crucible of unimaginable pressure. These cosmic collisions not only shape galaxies, but also fill them with the ingredients for planets and life. Every atom in
the iron in our blood, the calcium in our bones, the oxygen we breathe, all were born in stellar cores and released in supernova explosions. To study the life and death of stars is to study our own origins. Yet, for all we understand, many mysteries remain. We still do not fully grasp how stars evolve under extreme conditions, or how some of the earliest stars, massive and short-lived, gave rise to the first black holes. Observations of distant galaxies suggest that black holes and their host galaxies grew together, each influencing the other's formation. But the details of this cosmic relationship are still hidden behind veils of time and dust. At the largest scales, black holes serve as the engines of galactic evolution. The energy they release can regulate the growth of galaxies, controlling how fast stars are born and how quickly they die. Without them, galaxies might form too many stars too quickly, exhausting their gas and collapsing under their own weight. With them, the process is balanced, a cycle of creation and restraint that allows the universe to endure for billions of years. The connection between black holes and star formation extends even to the smallest scales. The same gravitational principles that shape galaxies also govern the birth of new stars within molecular clouds. Gravity is both the destroyer and the creator, compressing gas to form stars and collapsing stars to form black holes. It is the single force that unites every stage of this cosmic story. As we observe the night sky, we witness these processes unfolding on unimaginable timescales. Stars that appear steady and eternal to us are in truth constantly changing. Some are just beginning their journey, others are nearing their end. And somewhere among them, hidden by distance and darkness, black holes wait, silent reminders of what happens when gravity takes everything to its ultimate limit. As stars die and black holes are born, their stories do not end in isolation. The cosmos is interconnected. Every birth, every collapse, every merger ripples outward, leaving an imprint that will shape other stars and galaxies for billions of years. When a massive star collapses into a black hole, it doesn't vanish from the fabric of the universe. Its gravity remains, influencing nearby stars, planets, and gas clouds. In many systems, the dead star becomes part of a binary pair, two stellar remnants orbiting each other, one often a black hole and the other still burning. These binary systems are laboratories for understanding extreme physics. The black hole, though invisible, exerts an undeniable pull. As its companion evolves and expands, material begins to drift across the gap between them. The gas spirals inward, forming an accretion disk that glows with intense radiation as friction and gravity heat it to millions of degrees. Even though the black hole itself emits no light, the disk around it shines brightly, revealing its presence. X-ray telescopes detect these signals, allowing astronomers to measure the mass and spin of the black hole. The rhythm of these emissions, the flicker and pulse of the radiation, tells us how matter behaves at the edge of physical law. The more we observe, the more we realize how diverse these systems are. Some are calm and steady, feeding slowly over thousands of years. Others flare suddenly, consuming large amounts of matter in a brief, violent burst. Each one contributes to our understanding of how black holes grow and how they interact with their surroundings. In galaxies across the cosmos, the same story unfolds on grander scales. At the centers of galaxies, supermassive black holes feed on the material drawn inward by their gravity. Around them, vast disks of gas and dust rotate at incredible speeds. When these black holes are active, the energy released can outshine all the stars in the galaxy combined. Astronomers believe that many of these supermassive black holes were born from smaller ones, the remnants of the first stars. Over billions of years, through a process of accretion and mergers, they grew to colossal proportions. Some may have formed directly from collapsing clouds of primordial gas, bypassing the stellar phase altogether. In either case, black holes have been central to the universe's evolution since its earliest days. They serve as both endpoints and catalysts, marking the transition between the life of stars and the shaping of galaxies. When two black holes orbit each other, they gradually lose energy through gravitational waves, ripples in spacetime itself. These waves carry information about the masses and orbits of the merging objects, allowing scientists to listen to events occurring billions of light years away. When the black holes finally collide, they merge into one, releasing a burst of gravitational energy greater than all the light from all the stars in the observable universe, but for a fraction of a second. Such events were once purely theoretical, predicted by Einstein's general theory of relativity. But in 2015, humanity detected them directly for the first time. The LIGO Observatory recorded the faint tremor of spacetime produced by the merger of two stellar mass black holes more than 1 billion light-years from Earth. It was a confirmation that the universe speaks not only in light, but also in gravity. Gravitational waves have opened a new window into the cosmos. Through them we can now study systems that are otherwise invisible.
We can learn how often black holes form and merge, how massive they become, and what role they play in shaping galaxies. Each detection adds to our growing picture of a universe filled with unseen motion and quiet power. The discovery of gravitational waves also connects back to the story of stellar life and death. Every wave we detect is a record of stars that once lived, burned, and collapsed. The merging of black holes is the final echo of their existence, the last step in a process that began in stellar nurseries billions of years ago. Stars and black holes are not separate phenomena, they are part of one continuous cycle. The birth of stars enriches the universe with light and elements. Their deaths enrich it with gravity, energy, and complexity. Without black holes, the universe would lack the balance that governs its structure. Without stars, there would be no matter for black holes to shape. In some cases, entire clusters of stars can form around a massive black hole. The dense gravitational environment influences how stars move and evolve. Over time, collisions and interactions can send stars spiraling inward, feeding the central black hole and increasing its mass. This dynamic interplay may explain how supermassive black holes grew so rapidly in the early universe. In these dense regions, the balance between light and gravity becomes intricate. Radiation from the accretion disk can push gas outward, while gravity tries to pull it back in. The result is a feedback loop that determines how quickly a black hole grows. Too much radiation and the gas escapes, too little and the black hole starves. Nature finds a balance that allows both the black hole and its host galaxy.
Evidence for this balance can be seen in the relationship between the mass of a galaxy's central black hole and the mass of its bulge, the dense region of stars surrounding it. The larger the bulge, the larger the black hole. This correlation suggests that galaxies and their black holes evolved together, influencing one another across billions of years. This idea that galaxies and black holes co-evolve is one of the most important discoveries in modern astrophysics. It shows that black holes are not merely the remnants of dead stars, but active participants in cosmic evolution. Their energy regulates star formation, their gravity sculpts galaxies, and their growth mirrors the growth of the universe itself. Yet even with this understanding, mysteries remain. How did the first supermassive black holes form so quickly after the Big Bang? How does matter behave under the extreme conditions near their event horizons? And what happens inside, where our current physics can no longer describe reality? These questions drive astronomers and physicists to keep searching, observing, and theorizing. Every new telescope, every new detection, brings us closer to understanding the connection between the life of stars and the dark hearts they leave behind. The story of stellar death is, paradoxically, a story of creation. The heavy elements scattered by supernovae form the raw material for new stars, planets, and eventually life itself. The gravitational forces unleashed by collapsing stars shape galaxies and influence cosmic structure. In every sense, the universe thrives on transformation. As we trace this cycle across the cosmos, we come to see black holes not as voids or destroyers, but as essential components of cosmic balance. They represent what happens when nature pushes its own laws to their limits. When a black hole forms, it preserves the mass, charge, and angular momentum of the star that created it. Nothing else escapes. The information about the star's inner structure seems to vanish, replaced by a perfect simplicity. Each black hole is defined by just a few properties, yet it influences the space around it for eternity. These remnants are timeless. Long after the last stars have burned out, black holes will remain, slowly merging and evaporating over incomprehensible timescales. In a distant future, when the universe is cold and dark, black holes may be the final sources of energy, their slow decay marking the ultimate end of the cosmic story. But for now, they are the beating hearts of galaxies. They remind us that death and creation are intertwined at every scale of the universe. In studying them, we learn about the life cycle of stars, the formation of elements, and the structure of space and time itself. We learn about our own origins, because every atom we are made of once belonged to a star,
and every star will one day return its matter to the cosmos. The life of a star is a balance between gravity and fusion. The death of a star is a surrender to gravity's will. Out of that surrender comes something new, a black hole, a neutron star, a cloud of gas and dust that will one day ignite again. Imagine drifting through the quiet vastness of space. The stars are thin now, scattered like grains of light on an endless black sea. Ahead lies something darker still, a region where the night itself deepens, where even starlight bends away and time itself begins to falter. This is the realm of the black hole, the deepest abyss known to science. From a distance, a black hole might appear serene, a perfect sphere of darkness surrounded by a faint halo of light. But the stillness is an illusion. Near it, the universe behaves in ways that defy ordinary experience. The familiar rules of space and time begin to stretch, twist, and finally break. The boundary between the known universe and this gravitational void is called the event horizon. It is not a surface in the traditional sense, no solid edge, no tangible wall. It is a threshold. Once crossed, nothing can escape. Not light, not matter, not even information. The event horizon is the ultimate one-way passage. To an outside observer, anything that falls toward it appears to slow down, moving ever more sluggishly as it nears the edge. The light it emits becomes redder and dimmer, fading into darkness. To the falling object, however, nothing unusual seems to happen at that precise moment. It passes the boundary without sensation, unaware that escape has become impossible. This strange difference in perception comes from the nature of space-time itself. Albert Einstein's general theory of relativity taught us that gravity is not a force in the traditional sense, but a curvature, a bending of the very fabric of space and time by mass and energy. A black hole is the most extreme expression of that curvature. The closer one gets, the more severely time slows and space distorts. For an observer far away, time near a black hole appears to almost stop. A star falling in seems frozen at the edge, its light stretched thin until it vanishes. Yet from the star's own perspective, time continues normally. It crosses the horizon and plunges inward, never to return. Both views are correct, each from its own frame of reference, a reminder that in the universe, reality is not always absolute. To approach a black hole is to enter a realm where our intuitions about motion, light, and even causality begin to unravel. The equations of relativity describe these effects with precision, yet they remain almost impossible to visualize fully. The curvature of space-time is not something we can see, it is something we must imagine, a geometry of existence itself. If one were to venture toward a stellar mass black hole, the journey would end quickly and violently. Long before reaching the horizon, the tidal forces, the differences in gravity between one end of your body and the other, would stretch and compress you in opposite directions. Astronomers call this process spaghettification. It sounds whimsical, but it describes one of the most brutal realities in the cosmos. The gravitational pull at your feet would be immensely stronger than at your head. The difference would grow so extreme that even atoms could be torn apart. For small black holes, this tidal destruction happens well outside the event horizon. For supermassive black holes, however, the horizon is so vast that the gradient of gravity near it is gentle. You could, in theory, cross the boundary intact, though escape would still be impossible. Inside the horizon, all directions point inward. The concept of away from the black hole no longer exists. Space and time trade roles. Moving forward in time becomes equivalent to moving deeper into the black hole. No force, no propulsion, no signal can turn you back. What lies at the center, beyond all resistance, is what physicists call the singularity, a point, or perhaps a region, where density becomes infinite and the known laws of physics cease to function. Here, our current theories cannot describe what happens. The equations of general relativity break down, and quantum mechanics, the physics of the very small, offers no complete answer. For decades, scientists have sought a way to reconcile these two pillars of modern physics. The unification of relativity and quantum theory could reveal what truly exists at a black hole's core. Some suspect the singularity might not be a point at all, but a region where space-time is violently curved yet finite.
Others propose that quantum effects could prevent complete collapse, creating a core of dense, exotic matter. Still others suggest that the singularity is not a thing, but a boundary in time, a place where our concept of before and after loses meaning. Black holes are not simply cosmic curiosities, they are
Within them, gravity reaches its maximum strength, matter reaches its ultimate density, and time itself flows toward an end. Yet, paradoxically, black holes also help us understand the universe at large. Their existence confirms that spacetime can bend, fold, and even trap light. They are the proof that Einstein's equations were not just mathematical abstractions, but descriptions of real, tangible phenomena. Despite their reputation as destroyers, black holes are also among the most precise and predictable objects in the universe. When described mathematically, a black hole can be completely characterized by just a few quantities: its mass, spin, and electric charge. This is known as the no-hair theorem. It means that all the complex details of whatever fell into the black hole, stars, gas, entire planets, are erased, leaving only these fundamental properties behind. To outside observers, two black holes of identical mass, spin, and charge are indistinguishable. The universe forgets their pasts. This simplicity is both elegant and unsettling. It implies that information, the fine details of matter's arrangement, is lost when a black hole forms. But according to the principles of quantum mechanics, information should never be destroyed. This apparent contradiction gives rise to one of the most profound puzzles in modern physics, the black hole information paradox. Physicists have debated this paradox for decades. If information truly disappears into a black hole, it would violate the basic laws of quantum theory. Yet, if information somehow escapes, how does it do so from a region that traps even light? The answer may lie in the subtle interplay between gravity and quantum effects. In 1974, physicist Stephen Hawking made a groundbreaking discovery. He showed that black holes are not completely black. They emit a faint radiation due to quantum processes near the event horizon. This phenomenon, known as Hawking radiation, arises when virtual particle pairs that constantly appear and vanish in empty space are separated by the black hole's gravity. One particle falls in while the other escapes. To an outside observer, it appears as though the black hole is radiating energy. Over immense timescales, this radiation causes the black hole to lose mass, gradually evaporating until eventually it may vanish entirely. If black holes can evaporate, what happens to the information inside them? Does it escape in the radiation, encoded in subtle correlations we cannot yet detect? Or is it preserved in some way beyond our current understanding? This remains one of the deepest questions in theoretical physics. Entire fields of research, quantum gravity, string theory, holography, have emerged in part to answer it. Some theories suggest that the information is not lost, but stored holographically on the event horizon itself. In this view, the three-dimensional contents of a black hole could be represented as a two-dimensional pattern on its surface. This concept has inspired a broader idea that the entire universe might function like a hologram, where the true information of our reality is encoded on a distant cosmic boundary. Such ideas stretch the limits of imagination, yet they may be essential to understanding how the universe truly works. Black holes, once thought of only as traps of destruction, may hold the key to a new, unified theory of physics. From the outside, a black hole appears silent and still, but in reality, its surroundings are among the most dynamic regions in space. The accretion disk, a swirling, luminous ring of gas and dust spiraling inward, can reach temperatures of millions of degrees.
Magnetic fields twist and snap, launching jets of plasma that shoot out from the black hole's poles at nearly the speed of light. These relativistic jets can stretch across thousands of light years, carrying energy far beyond the galaxy that hosts them. They shape their cosmic neighborhoods, compressing gas clouds, triggering or halting star formation, and influencing the growth of entire galaxies. Despite being born from collapse, black holes are engines of creation on galactic scales. They regulate the flow of matter, the birth of stars, and the structure of the universe itself. Even now, astronomers are studying them in unprecedented detail. The Event Horizon Telescope, a global network of observatories, captured the first image of a black hole's shadow in 2019, a supermassive black hole at the center of the galaxy M87. The image revealed the silhouette of the event horizon surrounded by a glowing ring of hot plasma. It was the first direct visual proof that these objects truly exist as Einstein predicted. Behind that glowing ring lies the abyss, silent, cold, absolute. The light that orbits near the event horizon does so in strange, looping paths. Some photons circle multiple times before escaping, creating a bright ring known as the photon sphere. Deeper still, light can no longer find a path out. If you could hover near that boundary, if somehow you could resist the pull, you would see the universe in a way no human has ever experienced. The sky would appear distorted, stars stretched and duplicated by gravitational lensing. Behind you, the rest of the universe would be compressed into a shrinking patch of light, all of time appearing to speed up as you watched from the edge of eternity. And if you were to fall in, your journey would be swift but strange. You would see the outside universe fade and accelerate, the passage of eons compressed into moments. To those watching from far away, you would seem to freeze at the horizon, fading into darkness. To you, the descent would continue, faster, deeper, until space itself became your direction of time. What happens after that, after the crossing, no one truly knows. As the plunge continues beyond the event horizon, the universe outside fades into irrelevance. The stars, the galaxies, even the concept of outside ceases to have meaning. There is only inward motion, not through space, but through time itself. Inside a black hole, geometry is destiny. What was once space becomes a direction in time, and what was once time becomes space. Every path leads inexorably toward the center, just as every moment leads inexorably toward the future. It is not a place you can escape from, not because you are trapped by a wall, but because the laws of reality themselves insist upon your descent. Here, the curvature of spacetime grows steeper and more chaotic. Any light emitted in this realm never reaches the outer world. It is bent back, trapped, devoured by the fabric of the whole. Even if your ship carried an infinite source of energy, no signal could pass through the horizon. The black hole does not merely hide what falls within, it isolates it from the rest of existence. Yet, paradoxically, black holes are also regions of immense order. Their structure can be described with astonishing simplicity. In their perfection, they are the ultimate geometric object of nature, spheres of warped space-time defined by a few simple quantities. They are not chaotic in themselves, rather they are the purest outcome of gravitational law. Still, what happens at their core remains one of the greatest unsolved mysteries in physics. As you move closer to what theory calls the singularity, matter is compressed beyond all known limits. Electrons, protons, and neutrons, the building blocks of atoms, are crushed together into forms of matter that cannot exist anywhere else in the universe. Even these may not survive. They may dissolve into energy, into a sea of quantum uncertainty, where space-time itself
fluctuates wildly. Our equations cannot yet follow you here. Relativity describes how space-time bends, but it cannot handle the infinite densities that the singularity implies. Quantum mechanics describes the behavior of particles on tiny scales, but it says
The two great theories of modern physics speak different languages, and inside a black hole, both must be true at once. To truly understand this region, we would need a unified theory, one that merges gravity with quantum mechanics into a single coherent framework. Physicists call this elusive idea quantum gravity. It might reveal that the singularity is not an infinite point at all, but a region of finite size and incredible complexity, governed by laws we have not yet discovered. Some ideas suggest that the core of a black hole could be a bridge to another region of space-time, what we call a wormhole. In the equations of general relativity, certain solutions describe tunnels connecting distant points in the universe. In theory, a black hole could serve as one mouth of such a tunnel, with a corresponding white hole, a region where matter and light are expelled instead of trapped at the other end. But these solutions may be mathematical curiosities rather than physical realities. Wormholes, if they exist, would be unstable. They might collapse instantly under their own gravity. Others propose that exotic forms of matter with negative energy could hold them open, but such materials remain hypothetical. Still, the idea persists because it captures something profound about black holes, that they are not merely objects, but regions of space-time itself, capable of bending reality in ways we can scarcely imagine. Whether or not wormholes exist, the equations hint that black holes may connect distant parts of the universe in unexpected ways. Time behaves strangely in these depths. To the falling observer, the descent to the center may take only seconds. To the universe outside, that same fall might stretch into infinity. The black hole becomes a time machine of sorts, not one that allows you to travel backward, but one that reveals the relativity of time itself. Einstein's insight that time is woven into space means that gravity is not just about attraction, it is about the flow of moments. The stronger the gravity, the slower time runs. Near a black hole, this effect becomes extreme. If you could orbit safely just outside the event horizon, you would experience time at a vastly different rate from the rest of the cosmos. A single hour for you could correspond to years, even centuries for the outside universe. This is not speculation, it is the direct consequence of the geometry of space-time. In a sense, black holes allow us to glimpse the structure of time itself. They remind us that the universe is not static, but dynamic and relative, its rhythms shaped by mass and motion. Inside the abyss, however, those rhythms end. Time's arrow points only one way, toward the singularity. There is no turning back, no orbit, no pause. Even light, the fastest thing in existence, is drawn inward. It does not fall in the way matter does. Rather, space-time itself carries it. Some theories imagine that at the core of a black hole, the universe might begin anew. The immense pressure and density could, in principle, trigger a rebound, a kind of cosmic bounce, where the collapse of matter in one universe becomes the birth of another. In this view, our own Big Bang might have been the result of such an event, the interior of a black hole from a parent universe giving rise to our own. It is a speculative idea, but one that captures the strange symmetry of existence. Black holes may not only mark the end of matter and energy, but also serve as seeds of creation. When we look at them, we are not only seeing destruction,
but transformation. The matter that falls in does not vanish. It is converted into energy, curvature, and perhaps new beginnings in ways we cannot yet perceive. The study of black holes has also forced physicists to rethink the nature of information itself. In quantum mechanics, every physical system carries information about its state, the arrangement and behavior of its particles. When a black hole forms, that information seems to disappear. But if information is truly lost, the fundamental predictability of quantum theory breaks down. Some researchers, including Stephen Hawking, initially believed that black holes destroyed information. Others, notably Leonard Susskind and Gerard 't Hooft, argued that information must somehow survive, encoded in subtle quantum fluctuations at the event horizon. This led to the idea of holographic duality, a principle suggesting that everything inside a region of space can be described by data on its boundary. In this way, a black hole becomes a literal hologram, a two-dimensional surface holding the full record of the three-dimensional world. This idea has expanded far beyond black holes themselves. It has led to the bold hypothesis that our entire universe may function in a similar way, its deepest reality existing not in three dimensions, but on a vast cosmic boundary, whose patterns give rise to everything we perceive. Such ideas are not metaphors, they are serious attempts to reconcile quantum physics and gravity. The mathematics suggests that the universe might be fundamentally informational, a vast, interconnected web where space, time, and matter are emergent properties of something deeper. If that is true, then black holes are the ultimate testing ground for this cosmic code. They are nature's most extreme experiments in information, energy, and geometry. Each one is a puzzle written into the fabric of the cosmos, a question about the ultimate limits of knowledge itself. And yet, for all their mystery, black holes are real, observable, measurable. We can detect their influence on nearby stars, their accretion disks shining in X-rays, their mergers echoing through space as gravitational waves. These signals are not theoretical, they are the music of the universe, ripples in space-time that confirm what once existed only on paper. When two black holes collide, the energy released in gravitational waves can exceed that of all the stars in the universe combined, but only for an instant. That energy ripples outward, stretching and squeezing space-time itself. In 2015, the LIGO Observatory detected these ripples for the first time, confirming Einstein's century-old prediction and opening a new window on the cosmos. Each detection since then has told us more about black holes, their masses, their spins, their population across the universe. These signals allow us to study black holes not by light, but by sound, the sound of gravity itself. Listening to those waves, we are hearing the heartbeat of space-time. For all their enormity, black holes are not isolated oddities. They shape galaxies, influence the birth of stars, and may even play a role in the evolution of life. Without the massive black hole at the center of our own Milky Way, the structure of the galaxy might never have stabilized. The balance between gravity and radiation that black holes impose helps regulate cosmic environments. They are destroyers and creators in equal measure. If one could hover safely near the horizon of a supermassive black hole, 1 millions or billions of times the mass of the Sun, the view would be breathtaking. The disk of infalling matter would blaze with radiation, swirling in slow motion due to the immense warping of time.
the surrounding stars would appear distorted, stretched into arcs and rings by gravitational lensing. Behind the black hole, the universe itself would seem to wrap around, a visual echo of reality bent back upon itself. To gaze upon such a sight would be to witness the power of gravity in its purest form, not as a pull, but as a sculptor of reality. In their silence, black holes remind us that the universe is not always loud or chaotic. Some of its greatest mysteries lie in stillness, in the places where light fails and time pauses. They are monuments to gravity's final triumph, yet also to human curiosity. For even
every observation, every theory, every mathematical refinement brings us closer to understanding not just what lies inside them, but what they say about existence itself. Perhaps black holes are the universe's way of testing our limits, asking how far we are willing to go in pursuit of truth and how much we can imagine beyond what we can see. The abyss is not merely a void, it is a mirror. When we look into it, we see not only the end of matter and time, but the depth of our own desire to know. In the quiet immensity of the universe, black holes are often imagined as isolated monsters, devouring, consuming, erasing everything that strays too close. Yet when we look deeper, a more intricate picture emerges. These objects are not merely destroyers, they are architects. They shape galaxies. They sculpt the flow of matter and energy. They influence the birth of stars and the evolution of cosmic structure itself. To understand the universe as it exists today, we must understand the silent role black holes have played since its earliest moments. Every galaxy we know of, from the smallest dwarfs to the grandest spirals, appears to have a supermassive black hole at its center. These cosmic anchors can weigh millions or even billions of times the mass of our Sun. Their gravitational influence extends far beyond their immediate surroundings. They sit at the heart of everything, like gravitational monarchs around which galaxies orbit and evolve. In the beginning, however, they were not so massive. The first black holes likely formed only a few 100 million years after the Big Bang, born from the deaths of the universe's earliest stars. These primordial giants, enormous short-lived stars composed mostly of hydrogen and helium, ended their lives in cataclysmic collapses, leaving behind black holes perhaps tens or hundreds of times the mass of the Sun. Over billions of years, these small seeds grew. They consumed gas and dust, merged with one another, and drew in surrounding matter. Every merger released gravitational waves, every feeding frenzy lit up the cosmos with radiation. Eventually, they grew into the supermassive black holes we observe at the cores of galaxies today. Their growth is not passive. When a black hole consumes matter, it does not simply swallow it whole. Much of the material spirals inward first, forming an accretion disk, a vast, luminous maelstrom heated by friction and gravity to millions of degrees. This disk radiates energy across the electromagnetic spectrum, from radio waves to X-rays. Sometimes magnetic fields near the black hole twist the plasma into tight columns and eject it outward at nearly the speed of light. These relativistic jets can pierce through entire galaxies, traveling for thousands or even millions of light years. Such jets are among the most powerful phenomena in nature. They carry tremendous energy and momentum, sweeping through interstellar gas, heating it and preventing it from collapsing into new stars. Paradoxically, this destructive power helps maintain balance within galaxies. Without it, galaxies might form too many stars too quickly, burning through their fuel and fading prematurely. In this way, black holes regulate the growth of galaxies, acting like thermostats for cosmic ecosystems. Their energy output, though concentrated near the center, reaches across vast distances, influencing structures many thousands of times larger than the black holes themselves. Astronomers call this process feedback, the dynamic interplay between black holes and their host galaxies. When a black hole feeds, it can drive winds and radiation that shape its surroundings. When it goes quiet, stars can form again in the cooled gas. This cycle of feeding and quiescence creates the rhythm of galactic evolution. It is remarkable to think that a single object hidden behind an event horizon smaller than our solar system can determine the fate of a galaxy spanning hundreds of thousands of light years.
The connection between a black hole and its galaxy is so strong that their properties are intertwined. Observations show that the mass of a galaxy's central black hole is closely related to the mass of its surrounding bulge of stars. The larger the galaxy, the more massive its black hole. This correlation suggests a deep and ancient relationship, a coevolution written into the very fabric of cosmic history. But how could something so small relative to the galaxy exert such vast influence? The answer lies in the energy released by accretion. When matter falls toward a black hole, it releases far more energy per unit mass than any other known process. A single gram of material falling into a black hole can emit as much energy as thousands of tons of TNT. Scaled up to galactic proportions, this makes the central regions of some galaxies among the brightest objects in the universe. In the early cosmos, when galaxies were young and gas was abundant, this process created quasars, intensely luminous beacons powered by supermassive black holes feeding at a furious rate. Quasars outshone their host galaxies by factors of hundreds, even thousands. From billions of light years away, we can still see their light today, ancient messages from an era when the universe itself was in its adolescence. Each quasar is a window into a time when black holes were rapidly growing, shaping the galaxies around them through immense radiation and outflows. The light we see from them has traveled across nearly the entire history of the universe to reach us. Over time, as galaxies matured and their central gas supplies thinned, most black holes quieted. The blazing quasars faded, leaving behind dormant giants like the one at the center of our own Milky Way, Sagittarius A star. Though quiet by cosmic standards, even Sagittarius A star still holds sway over its galactic domain. Its mass, roughly 4 million times that of the Sun, dictates the orbits of stars in the central region of the Milky Way. Every 16 years, one star, known as S2, completes a full orbit around it, racing through space at a few percent of the speed of light. From such observations, astronomers have been able to measure the mass of Sagittarius A star and confirm that its gravitational field behaves exactly as Einstein's equations predict. It is, without doubt, a supermassive black hole. Yet for all their size, these objects are astonishingly compact. Sagittarius A star would fit comfortably inside the orbit of Mercury. A black hole 1 billion times the Sun's mass could fit within our solar system. They are dense beyond comprehension, yet their effects are written across the sky in the form of galactic structure, starlight, and cosmic balance. When galaxies collide, as they often do, their central black holes spiral toward one another in a slow dance lasting millions of years. Eventually they merge, releasing a colossal burst of gravitational waves that ripple through the universe. These cosmic mergers not only create larger black holes, but also send shock waves through the fabric of space itself. In the distant future, such mergers will continue, building ever larger and rarer black holes. Over eons, the universe may evolve into a landscape dominated by a few enormous galaxies, each containing a single monstrous black hole at its heart. But even the mightiest of these giants are not eternal. According to Stephen Hawking's theory of black hole radiation, they too will eventually evaporate. Not quickly, but over timescales so vast they defy comprehension. A stellar mass black hole might take 10 to the 67 years to vanish. A supermassive black hole could endure for 10 to the 100 years or more, far longer than the current age of the universe.
As the cosmos continues to expand and cool, stars will burn out, galaxies will fade, and only black holes will remain. They will be the final monuments of matter, the last actors in the cosmic drama. And then, even they will begin to fade. Their Hawking radiation will grow stronger as their mass decreases. In their final moments, they will release bursts of energy, tiny flashes of the universe's last light.
Afterward, there will be only darkness, silence, and the cold geometry of empty space. This distant era, sometimes called the black hole epoch, will mark the universe's long descent into entropy, a time when all structure dissolves and the cosmos reaches thermal equilibrium. It is a poetic symmetry. Black holes, born from the collapse of order, will one day define the end of all order. Yet their role is not merely to consume. Through their influence, black holes have helped give rise to stars, galaxies, and even the conditions for life. The heavy elements forged in supernovae, carbon, oxygen, iron, are distributed through space in part by the energetic feedback that black holes drive. The same violent processes that can sterilize regions of space also enrich others. In this way, the story of black holes is also the story of creation. They are reminders that destruction and genesis are two sides of the same cosmic coin, that in the universe, endings are often beginnings in disguise. The collapse of a star gives birth to a black hole. The black hole's energy sculpts the galaxy. The galaxy's stability allows stars to form, and within those stars, the elements of life emerge. To look at the night sky, filled with billions of galaxies, is to see the legacy of black holes written in starlight. Each spark of light carries the imprint of their influence, the subtle signature of gravity's deepest expression. In the early universe, before galaxies took shape, black holes may have played a key role in gathering matter together. Their immense pull could have drawn gas and dark matter into dense regions, acting as seeds for the first galactic structures. Without them, the universe might have remained a diffuse, featureless expanse. As cosmic time unfolded, black holes became the anchors around which galaxies stabilized. Their feedback determined how quickly stars formed, how long gas persisted, and how bright galaxies could shine. They are not separate from the universe's evolution, they are central to it. Even now, as we peer into the most distant reaches of space, the faint light we capture carries echoes of black holes that existed more than 13 billion years ago. Each one tells a piece of the story, how the cosmos grew from simplicity to complexity, from darkness to the web of light we see today. The universe we inhabit owes its shape, its rhythm, and much of its beauty to these silent gravitational engines. They are not merely features within the universe, they are part of its scaffolding. Their presence helps determine how galaxies align, how they merge, and how they evolve through time. When two galaxies approach one another, tidal forces stretch them apart, scattering stars and gas across the void. But their central black holes, like two invisible beacons, are drawn together. They spiral inward, shedding energy through gravitational waves, until at last they collide and merge into a larger, more powerful singularity. These cosmic unions are not rare events. They have shaped the universe again and again throughout billions of years. Each merger is a chapter in the long story of growth and transformation, a reminder that creation and destruction are inseparable in the cosmic dance. And yet, despite their enormity, black holes are astonishingly efficient. They waste almost nothing. When matter falls into them, up to 40% of its rest mass can be converted into energy, far more than any process that fuels stars. This efficiency makes them both the brightest and the darkest objects in existence, blazing in their accretion, silent in their cores. From the centers of galaxies, black holes send out powerful winds, jets, and radiation that sculpt the cosmic environment. These flows of energy regulate the formation of stars, redistributing matter and heat across the interstellar medium. Without such feedback, galaxies might become unstable or collapse into themselves. In this sense, Black holes act as engines of equilibrium. They are the cosmic regulators, ensuring that the universe does not burn too brightly or fade too soon. Their destructive power becomes a source of stability, a balance between order and chaos. Even their gravitational pull plays a subtle role in maintaining structure. As galaxies orbit within clusters, their black holes add to the total mass that binds these colossal systems together. The interplay of dark matter, stars, gas, and black holes forms a dynamic web that keeps the universe cohesive on scales far beyond our comprehension. And yet, black holes also challenge our understanding of reality itself. They show us where our theories reach their limits, where the known laws of physics give way to the unknown. At the edge of a black hole, general relativity and quantum mechanics collide. The curvature of spacetime becomes infinite, and the smallest fluctuations in energy can no longer be ignored. This is where science reaches its horizon, a boundary not of space, but of knowledge. Physicists believe that, to truly understand black holes, we must look beyond current theories. Perhaps spacetime is not continuous, but granular, made of discrete units, like pixels in a cosmic screen. In this view, black holes are windows into the quantum nature of the universe itself. String theory and loop quantum gravity, two leading frameworks for unifying physics, offer glimpses of how this might work. In these models, singularities could be replaced by finite, stable structures, a kind of quantum foam, where gravity and matter are inseparable. The interior of a black hole might then not be an end, but a transformation, a region where information and energy are reconfigured in.
If such a theory is ever confirmed, it would mean that black holes are not cosmic dead ends, but bridges, linking classical physics to the quantum world, matter to energy, and perhaps one universe to another. Even now, black holes are teaching us about the limits of time. In the far future, as stars die and galaxies fade, black holes will be among the last remaining sources of energy. Slowly, over unimaginable spans of time, they will radiate away their mass through Hawking radiation. One by one, they will vanish, leaving behind a universe without light, without warmth, without motion. This final state, the heat death of the universe, is the ultimate expression of entropy, the slow, inevitable spread of energy into uniformity. In that distant era, all distinctions will fade. There will be no stars, no galaxies, no black holes, only cold, diffuse particles drifting through an ever-expanding void. And yet, even in that silence, the legacy of black holes will remain. They will have shaped the path that led to that moment, having regulated galaxies, forged elements, and governed the very architecture of space. The universe will die, in part, because of the balance they maintained. Their story is also a mirror for our own. We too are made from the remnants of stars whose fates were intertwined with black holes. The carbon in our cells, the iron in our blood, the oxygen we breathe, all were forged in stellar furnaces that existed in galaxies shaped by black holes' invisible hands. Every atom within us carries the memory of gravitational cycles that stretch back to the dawn of time. To contemplate black holes is, in a sense, to contemplate our own origins. In the modern era, we continue to find new ways to study them. Telescopes that detect X-rays and radio waves reveal the behavior of matter as it spirals inward. Gravitational wave observatories listen for the faint tremors of distant mergers. Each discovery adds to our growing understanding, not just of black holes, but of the laws that govern everything. The Event Horizon Telescope's images of supermassive black holes, first in the galaxy M87, then at the heart of our own Milky Way, are more than scientific triumphs. They are moments of revelation. For the first time, we can see the silhouette of an event horizon,
the literal shadow of nothingness against a backdrop of light. That shadow is not merely an image, it is evidence that our theories of space-time are correct, that Einstein's vision of gravity bending light and time still holds even under the most extreme conditions. Each observation brings us closer to understanding how the universe functions on every scale, from quantum particles to the largest cosmic structures. But perhaps the most remarkable truth about black holes is that they do not simply exist in isolation. Their presence affects the cosmic story at every level. They are part of the balance between creation and decay, between expansion and collapse. They demonstrate that the universe is not static, but dynamic, forever transforming, forever balancing extremes. In this way, black holes are both the sculptors and the witnesses of cosmic evolution. They watch the rise and fall of galaxies, the birth and death of stars, the unfolding of time itself. And they remind us of a profound truth, that everything in the universe is connected by the same fabric of space-time, the same laws, the same forces, the same origin. From the smallest quantum fluctuation to the largest cluster of galaxies, all things move within this grand continuum. Black holes reveal its curvature, its strength, its fragility. They show us the unity of all existence. The next frontier of discovery lies not only in observing black holes, but in understanding what they mean. They may hold the key to reconciling the contradictions between relativity and quantum mechanics, between the infinite and the infinitesimal. In the pursuit of that knowledge, we are seeking not only the nature of black holes, but the nature of reality itself. To listen to the universe is to hear its quietest truths, the soft hum of gravity, the whisper of time bending, the echo of creation folded into darkness. Black holes are not the end of that story. They are its turning points, places where everything we know converges into mystery, and where mystery, in turn, becomes understanding. The universe is shaped by them, yet it also shapes them in return. They are partners in a cosmic dialogue that has been unfolding for billions of years. As we gaze deeper into the night sky, into regions where the faintest light struggles to reach us, we are not looking into emptiness. We are looking into history, into the living memory of creation itself. Somewhere far away, a black hole is feeding, its gravity pulling gas into a glowing spiral. Somewhere else, two black holes are merging, sending ripples through the fabric of space that will pass through our planet long after we are gone. And somewhere, perhaps at the edge of the observable universe, an ancient black hole from the dawn of time still waits, silent, immense, holding the memory of how everything began. They are the keepers of cosmic time, the silent hearts of galaxies, and perhaps the final storytellers of existence. To understand them is to understand the balance between creation and oblivion, the rhythm of a universe forever in motion, forever seeking equilibrium between light and shadow. Black holes do not end the story of the cosmos. They ensure that it continues, reshaped, renewed, reimagined across the vast, endless dark. The universe drifts quietly, expanding into the endless dark. Galaxies stretch farther apart, stars grow old, and light itself fades into the distance. And in the heart of what remains, black holes endure, the last bastions of gravity, the final engines of cosmic power. To understand the end of all things, we must understand them, because in the slow fading of the cosmos, black holes are not only destroyers, they are keepers of time, custodians of entropy, and perhaps the seeds of creation itself. When the last stars exhaust their fuel, when fusion can no longer ignite, the universe will grow colder, white dwarfs will dim, neutron stars will cool, and planets will drift unseen through the dark. In that far future, black holes will remain, silent, immense, and patient. They will feed on what is left: rogue planets, wandering debris, faint traces of gas. All will spiral inward over eons. As the universe stretches thinner, even collisions between black holes will become rare. The cosmos will grow quiet, governed only by the slow rhythm of gravity and decay. Eventually, there will be nothing left to consume. Black holes will become the final stage of structure in the universe, the last shape that gravity allows. But even they will not last forever. Stephen Hawking revealed one of the most astonishing truths of modern physics. Black holes are not truly black. They glow, faintly, invisibly, imperceptibly, through a process now known as Hawking radiation. According to quantum theory, the vacuum of space is not empty. It seethes with fleeting particles that appear and vanish in pairs, existing for mere moments before annihilating each other. Near the event horizon of a black hole, this delicate balance can be disturbed. One particle falls in, the other escapes. To an outside observer, it appears as though the black hole is emitting energy. Over immense timescales, this emission causes the black hole to lose mass. It shrinks, it fades, and eventually it disappears. This process is incredibly slow. For a black hole with the mass of our Sun, it would take 10 to the 67 years to evaporate completely.
For supermassive black holes, those that weigh billions of solar masses, the process would take even longer, perhaps 10 to the 100 years or more. By then, the universe as we know it will be gone. The stars will have vanished, the galaxies will have dissolved. Only the faint hum of fading black holes will remain, whispering the last words of a universe that once blazed with light. As they shrink, they grow hotter, radiating more intensely until, in their final moments, they burst in a brief flash of energy, a final exhalation into the cold. After that, nothing. Yet from this nothingness, we find profound questions. If black holes evaporate, what happens to the information they once contained? Does it vanish as well, or does the universe somehow preserve it? Every photon, every particle, every pattern of matter that ever fell within their grasp. This is the information paradox, one of the deepest mysteries in modern physics. According to quantum mechanics, information cannot be destroyed. It may change form, it may be scattered, but it must always remain encoded in some way. Yet black holes seem to defy this rule. When they evaporate, the matter they consumed appears to vanish from the universe forever. For decades, scientists have debated this contradiction. Some have proposed that information escapes slowly in the radiation itself. Others believe it remains imprinted on the event horizon, stored like a hologram, a concept known as the holographic principle, which suggests that all the information within a region of space can be represented on its boundary surface. If this is true, then our entire universe may behave like a hologram, a vast projection of information encoded on the fabric of spacetime itself. In that view, reality as we experience it could be a kind of cosmic illusion, a reflection of deeper principles we have yet to understand. Whether this is true or not, black holes remain our most direct link between the quantum world and the cosmic scale. They are the intersection of gravity, thermodynamics, and information, the ultimate laboratory for testing the nature of reality. In their study, we have learned that black holes have temperature, entropy, and energy, just like any thermodynamic system. Their entropy, a measure of disorder, is proportional to the surface area of their event horizon, not their volume. This relationship has reshaped how we think about the universe. It suggests that space itself may be made of information, that geometry and gravity emerge from the quantum structure of reality. When you consider this, it's hard not to feel awe.
Black holes are no longer just gravitational wells or cosmic traps. They are keys to understanding why anything exists at all. As the universe grows older, it will continue expanding. Dark energy, the mysterious force driving cosmic acceleration, will push galaxies ever farther apart. Eventually, even the faint light of distant stars will redshift beyond visibility. The night sky will grow empty, the Milky Way itself stretched and dimmed until only black holes remain. After trillions of years, even these giants will begin to evaporate. Their energy will disperse into the cold vacuum, adding the final trace of warmth to a dying cosmos. The universe will become smooth, uniform, and still. And then, silence. This is the farthest future we can imagine, the universe at maximum entropy, where no energy gradients remain, no motion, no difference, no time as we understand it. It is sometimes called the heat death, not an explosion, but a quiet dissolution into equilibrium. But the story may not end there. Some cosmologists propose that even this stillness is temporary, that fluctuations within the quantum vacuum could give rise to new beginnings. In that view, the death of one universe might seed another, born from the smallest ripple of energy in the emptiness. Perhaps every black hole that has ever existed contains the potential for a new cosmos within, a universe budding inside a universe, each connected by the mysterious geometry of spacetime. If that is true, then the end and the beginning are one and the same. The collapse of matter into a singularity might also be the birth of expansion elsewhere. The infinite density of a black hole could mirror the conditions of our own Big Bang, a bridge between cycles of creation. It's a breathtaking thought that our universe itself may have begun as the interior of a black hole in some greater cosmos. That every black hole could be a doorway not to oblivion, but to rebirth. Though we cannot yet prove this, it shows us something profound about the human spirit. We look into the darkest places not only to understand what ends, but to imagine what might begin again. When we study black holes, we are studying the boundaries of our knowledge, but we are also exploring the limits of imagination, the courage to ask what lies beyond what we can see. In that sense, black holes are both the most destructive and the most inspiring objects in the universe. They remind us that endings are never truly final. Every collapse carries within it the possibility of transformation.
When we look at black holes, we see more than cosmic phenomena. We see the reflection of our own curiosity, the endless drive to understand, to reach beyond what is known, to trace the contours of existence itself. For centuries, humanity has stared into the night sky, wondering what lies among the stars. Each generation has found new ways to see farther, to measure more precisely, to decode the faint whispers of light that have traveled billions of years to reach our eyes. And yet, for all our progress, black holes remind us that some things remain veiled in mystery. They represent the point where our equations break down, where time itself becomes a question. At their heart, the familiar laws of physics dissolve. Gravity, space, energy, and information merge into a single unknown. To cross that threshold would be to encounter reality in a form beyond our comprehension. But perhaps that is the true beauty of black holes. They preserve mystery in a universe increasingly mapped and measured. They remind us that not everything must be solved. Some truths must simply be witnessed, respected as part of the grand design that gives rise to stars, galaxies, and life itself. Our universe thrives on contrast, light and darkness, order and chaos, creation and destruction. These are not opposites, but partners, shaping one another in perpetual balance. Without collapse, there could be no birth. Without gravity's pull, there could be no gathering of matter, no galaxies, no stars to shine. And so, even in their silence, black holes sustain the cosmic rhythm.
They are the counterpoint to light, the deep notes that give the universe its harmony. When we imagine falling into one, it is tempting to see only annihilation, but from another perspective, it is an act of joining, merging with the very structure of space-time, becoming part of the geometry that holds everything together. In that sense, nothing truly disappears. Every particle, every photon, every piece of information becomes part of a greater pattern, rearranged, transformed, but never lost. This is the promise of physics, that even in the darkest places there is continuity, that beyond every horizon some form of existence persists. It may be that as black holes fade and the universe grows quiet, the last traces of their radiation will encode the entire history of what once was. Every orbit, every collapse, every spark of life. And in that fading glow, the memory of creation will linger. For us as observers living in a bright and dynamic age of the cosmos, these ideas stretch the imagination. We exist in a rare window of time when stars still burn, galaxies still collide, and the universe is young enough to be visible. Billions of years from now, no such view will remain. The sky will grow empty, and even the nearest galaxies will drift beyond reach. But for now, we can still see them. We can still learn, still wonder. We can trace the spirals of light around black holes, measure the gravitational ripples of their collisions, and hear the faint echoes of their power through instruments of unimaginable precision. Each discovery is an act of reverence, each measurement a kind of listening. Through them we hear the heartbeat of the universe. In that quiet pulse lies a lesson, that the universe, vast and indifferent as it may seem, is also a mirror. Its patterns reflect the same principles that govern us, cycles of creation, growth, and transformation. We too are temporary gatherings of matter shaped by gravity and time, destined one day to return to the silence from which we came. And yet, in that brief moment of existence, we are capable of understanding the cosmos itself. The atoms in our bodies were forged in stars. The forces that hold us together are the same that bind galaxies. To know black holes is to know a part of ourselves, the deepest, most mysterious part, where knowledge meets wonder. In this way, the study of black holes is also a meditation on being. It asks us to consider not just where we are, but what it means to exist within a universe that both creates and consumes. Perhaps the true lesson of black holes is humility.
They remind us that even our greatest achievements, our theories, our instruments, our understanding, reach a limit. Beyond that limit lies silence, and within that silence, possibility. As we continue to explore, our questions grow more profound. What is space, truly? What is time? Are they fundamental, or are they illusions born from deeper realities? Is the universe finite or infinite? And if it ends, will it begin again? In these questions lies the spirit of science, the same spirit that led humanity to light fires in the dark, to build telescopes, to send probes beyond the solar system, to look into the abyss and say, "I want to know." That desire is as much a part of the universe as the stars themselves. We are its way of knowing itself, consciousness emerging from matter, asking what it means to be. And black holes, paradoxically, may hold the answers to those questions. They contain the intersection of every law, the meeting point of opposites. They show us that the universe is both finite and infinite, both fragile and eternal, that within every end lies the seed of a beginning. In the distant future, when even the last black holes have faded, the universe may be empty, but the pattern they created, the invisible order of space-time, will remain. It will define the geometry of whatever comes next, just as the first black holes defined the structure of what we see now. If new universes are born from their remains, perhaps each carries echoes of the last, faint imprints of the physics that came before, like memories passed between worlds. And maybe, within one of those future universes, another civilization will look up at its sky, see the shadows of gravity, and wonder, just as we do now. That cycle of curiosity may be endless. It may be the universe's way of ensuring that knowledge and awe never vanish, only transform. And so, as we close our eyes and imagine the depths of space, the silent motion of galaxies, the invisible pull of black holes, we can find peace in knowing that everything is part of a vast, harmonious design. We are small, yes, but we are also connected. Every thought, every observation, every dream is part of a cosmic story that stretches beyond measure. When you gaze into the darkness, you are not looking into emptiness. You are looking into the heart of everything, the place where light and gravity meet, where time slows, and where the universe speaks in the language of silence. In that silence, all questions merge into one. What does it mean to exist? Black holes do not answer that question outright. They invite us to listen, to feel the pull of gravity not as a force, but as a reminder that everything is drawn together, bound by unseen threads of meaning. Perhaps that is why they fascinate us so deeply. They are both a mystery and a mirror, a paradox and a promise. They remind us that knowledge begins where certainty ends. And so we continue to learn, to listen, to dream. We send our instruments to the farthest reaches, our minds to the edge of understanding. Each discovery brings us closer, not to an ending, but to a deeper beginning. The universe is vast, its time is long, its silence is full of stories waiting to be heard, and among them, the story of black holes, their creation, their power, their quiet persistence, may be the most profound of all. For in them we see the unity of existence, how light and darkness, birth and death, matter and void all belong to the same infinite pattern. We may never cross an event horizon, we may never see what lies beyond, but in trying to understand, we already take the first step. We become part of the universe's search for itself. So as the stars drift across the sky and the night deepens around you, remember this: somewhere, across the vast gulf of time and space, a black hole turns, silent, patient, eternal, holding within it the memory of everything that ever was. And as you listen to the quiet rhythm of your own heartbeat, you are hearing the same pulse that moves galaxies and bends light, the pulse of gravity, the pulse of being. The universe breathes through us as we breathe it in return. It collapses and expands, forgets and remembers, dies and begins again. And so, even in the deepest darkness, there is always light waiting to be reborn.